Pull out your phone, open maps, get directions. Your phone knows exactly where you are, within meters, sometimes within centimeters. GPS, Global Positioning System. Satellites orbiting overhead sending signals. Your phone receives those signals, calculates distances, triangulates position. Simple. Except it's not simple, because those satellites are moving fast, about 14,000 kilometers per hour. And at that speed, time runs slower for them. Their clocks tick at a different rate than yours. If GPS didn't account for this, if it ignored relativity, your position would be wrong, off by kilometers, within hours. Your phone would be useless. This is not theoretical physics. This is engineering. Time dilation is real, measured, compensated for every single day in the device in your pocket. You age slower when you move, not metaphorically, literally. Your biological processes slow down, your heartbeat, your metabolism, your cellular decay, everything, not by much at walking speed. But the effect is real. The faster you move, the slower time passes for you relative to someone standing still. This is not an illusion, not a trick of measurement. Time itself runs at different rates depending on velocity. Einstein predicted this in 1905. Special relativity, one of its core predictions. Moving clocks run slow. At everyday speeds, the effect is tiny, unnoticeable, but it's there. And at high speeds, it becomes significant, measurable, unavoidable. Here's how it works. Time and space are not separate. They're woven together into space-time, a four-dimensional structure. You're always moving through space-time, always. But your motion is divided between space and time. If you're sitting still in space, all your motion is through time. You're moving into the future at maximum rate, 1 second per second. But if you start moving through space, you have to divert some of that motion away from time. You're now moving through space and time, which means you're moving through time more slowly. Think of it like this. You're walking north at a steady pace. That's your motion through time. Now you start walking northeast. Part of your motion is still north, but part is now east. You're covering less northward distance per step because some of your motion is diverted eastward. Same principle. When you move through space, you divert motion away from time. Time slows down for you. The math is precise. At low speeds, the effect is negligible. Walking, driving, flying, the time dilation is real but tiny, billionths of a second. But it's there, and it accumulates. GPS satellites orbit at about 14,000 kilometers per hour. At that speed, their clocks run slow by about 7 microseconds per day, 7 millionths of a second. Not much. But GPS relies on nanosecond precision, billionths of a second. A 7 microsecond error per day means position errors of several kilometers. Totally unacceptable. So GPS compensates. The satellite's clocks are programmed to tick slightly faster than they naturally would, by exactly the amount needed to cancel the time dilation effect. This is not speculation. This is built into the system. If you remove the relativity correction, GPS would fail. Immediately, measurably, within hours. Now let's talk about what this means. Time is not universal. There's no single time that everyone shares. Your time is your time. Someone else's time is different. If you're moving relative to them, your clocks run at different rates. Both clocks are correct. Both are measuring time accurately in their own frame. But they don't agree, because time itself is relative. Here's a thought experiment. The twin paradox. Two twins. One stays on Earth. The other gets on a spaceship, accelerates to near light speed, travels to a distant star, turns around, comes back. When they reunite, the traveling twin is younger, significantly younger, years younger, decades younger, depending on the speed and distance. This seems impossible. Both twins experience time normally. The traveling twin didn't feel time slowing down. Every second felt like a second, but fewer seconds passed. Less time elapsed. The traveler aged less, biologically, physically, actually younger. This has been tested, not with humans and spaceships, but with particles, muons, created in the upper atmosphere by cosmic rays. Muons are unstable. They decay. Their average lifetime is about 2 microseconds. In that time, even moving at near light speed, they should only travel about 600 meters before decaying. But we detect them at ground level. They've traveled over 10 kilometers. How? Time dilation. From our perspective, the muons are moving at near light speed. So their clocks run slow, their 2 microsecond lifetime is stretched. They live longer from our perspective, long enough to reach the ground. From the muons' perspective, their lifetime is still 2 microseconds, but the atmosphere is contracted, length contraction. Another relativistic effect, the distance to the ground is shorter in their frame. Either way, they reach the ground. Time dilation and length contraction are two sides of the same phenomenon. Now think about what this means for aging. Aging is a physical process. Cells dividing, proteins breaking down, DNA damage accumulating. All of this happens in time. If time runs slower, these processes happen slower. You age slower. Not subjectively, objectively, measurably. Astronauts on the International Space Station are moving fast, about 28,000 kilometers per hour. They're aging slower than people on Earth. Not by much. After a year in space, they're younger by about 0.01 seconds than they would have been on Earth. Tiny, but real, measured, verified. If you could travel at 99% the speed of light, time would run about 7 times slower for you. 1 year for you would be 7 years for Earth. You'd age 1 year, Earth would age 7. Come back after what feels like 10 years of travel. 70 years have passed on Earth. Everyone you knew is old or dead. You're barely aged. At 99.9% the speed of light, the factor is about 22. 1 year for you, 22 years for Earth. At 99.99%, comma, it's about 71. At 99.99%, comma, it's about 224. The closer you get to light speed, the more extreme the dilation. There's no mathematical limit. If you could reach exactly light speed, time would stop for you completely. No time would pass at all. You'd be frozen in the instant of departure. From your perspective, you'd arrive at your destination instantaneously, no matter how far away. For photons traveling at light speed, emission and absorption happen in the same instant. 0 time passes for light. But you can't reach light speed. You have mass. And accelerating mass to light speed requires infinite energy. Impossible. But you can get arbitrarily close, and the time dilation becomes arbitrarily large. You could travel to distant stars and galaxies. Decades for you. Centuries or millennia for Earth. Time dilation makes interstellar travel theoretically possible within a human lifetime. For the traveler. Not for those left behind. Now here's the disturbing part. This isn't symmetric. The traveling twin really is younger. It's not just that each twin sees the other's clock running slow. That would be symmetric. But acceleration breaks the symmetry. The traveling twin accelerates, turns around, decelerates, accelerates back, changes reference frames. That's not symmetric. The stay-at-home twin never accelerates, never changes frames. So when they reunite, the traveling twin is objectively younger. Less time has passed in their frame. Fewer heartbeats, fewer breaths, fewer cell divisions. Actually younger. This has been tested with atomic clocks on airplanes. Take 2 synchronized atomic clocks, leave one on the ground, put one on an airplane, fly around the world, land, compare. The flying clock is behind by nanoseconds, exactly as relativity predicts. The clock that moved is younger, less time passed for it. So every time you move, you age slower. Walk across the room. You age trillionths of a second less than someone standing still. Drive to work. Billionths of a second. Fly across the ocean. Nanoseconds. The effects are real. Just tiny at everyday speeds. But here's what's truly strange. This means there's no absolute time. No universal now. Your now is different from my now if we're in relative motion. Events that are simultaneous for you are not simultaneous for me. Time is local. Frame dependent. Imagine 2 events. Lightning strikes at 2 different locations. Far apart. Did they happen at the same time? Depends on who you ask. For someone at rest relative to the midpoint, they're simultaneous. For someone moving toward one of them, that one happened first. For someone moving the other direction, the other one happened first. All 3 perspectives are equally valid. There's no absolute answer. Now you might worry. This seems to break causality. If simultaneity is relative, can effects happen before causes in some frames? No. Causality is protected. Events that are causally connected, where one can influence the other, have an invariant order. Everyone agrees on the sequence. Light speed is the speed limit for cause and effect. Only events that are too far apart in space and too close in time to be causally connected can have ambiguous order. And those events can't influence each other anyway. The universe protects causality even while allowing relative simultaneity. This is the block universe view. Space-time is a four-dimensional structure. All of time exists simultaneously. Past, present, future. All equally real. Your experience of now is just your consciousness moving along your world line through space-time. But the whole structure exists, and different observers slice through it differently. Their now is a different slice than your now. If that's true, then aging slower when you move isn't about processes slowing down. It's about your path through space-time being shorter in the time direction. You take a different route. Both twins travel through space-time from departure to reunion, but they take different paths. The traveling twin's path is curved, bent by acceleration, and curved paths through space-time have different lengths and time. The traveling twin's path is shorter. Less proper time elapses. They age less. Proper time, that's the key concept. The time measured by a clock moving along a specific path through space-time. Different paths have different proper time. Straight paths have maximum proper time. Any deviation, any acceleration reduces proper time. Stay still, you maximize aging. Move and accelerate, you minimize aging. Your biological clock measures proper time along your world line, and that depends on your motion. You're aging slower right now. Earth is moving, orbiting the sun at 30 kilometers per second, rotating at about 460 meters per second at the equator. You're moving, so your clock runs slow, not relative to Earth. You're moving with Earth, but relative to the cosmic microwave background, the rest frame of the universe. In that frame you're moving, so you're aging slower than someone at rest in the CMB frame. The difference is tiny, unmeasurable for a human lifetime, but it's there, real. A pilot who flies for 40 years ages about 59 microseconds less than someone who stayed on the ground. A Formula One driver racing at 300 kilometers per hour ages slower during the race. An astronaut spending a year on the ISS ages 0.01 seconds less. These aren't theoretical calculations, these are measured effects. Real differences in elapsed time. Motion slows time. Always. For everyone. The only question is how much. At walking speed, the time dilation factor is essentially one so close to perfect one that it's completely negligible. At airplane speed a few hundred kilometers per hour, the factor is still essentially 1 but technically measurable with atomic clocks. At orbital speed about 28,000 kilometers per hour, the effect starts to matter for precision timing. At 1% the speed of light, you get a noticeable deviation. At 10%, it's about 0.5% slower. At 50% light speed, time runs 15% slower. At 90%, more than twice as slow. At 99% light speed, time runs 7 times slower. At 99.9%, 22 times slower. The curve is steep near light speed. Small increases in velocity produce huge increases in time dilation. This is why you can't reach light speed. As you approach it, time dilation approaches infinity. Your clock would stop from outside perspectives. This is real. GPS proves it every second. Muons prove it every time cosmic rays hit the atmosphere. Atomic clocks on airplanes prove it. Every high-energy particle accelerator proves it. Particles moving at near light speed live longer than they should based on their natural decay rates. Their internal clocks run slow, their decay is slowed. Time dilation. Measured, verified, used, relied upon in modern physics and engineering. So, your phone knows this. GPS satellites compensate for it every second. Particle physicists rely on it, and you experience it constantly. Walking, driving, flying, every motion slows your clock. Imperceptibly at everyday speeds, but measurably at high velocities. You are aging slower when you move, right now, because Earth is moving. You're in motion. Time is dilating. Your biological clock runs slow, by amounts too small to notice in a human lifetime, but real, inevitable, universal. And if you could move fast enough, near light speed, you could age decades while Earth ages millennia. You could witness the far future. Not by living forever, by living slowly while the universe lives fast. Time is not absolute. Time is not universal. Time depends on velocity, your motion, your path through space-time. And that path determines how fast you age, how many seconds you experience, how much time passes for you compared to the universe around you. Your GPS knows this. The satellites orbiting overhead are programmed with Einstein's equations, compensating for time dilation every moment. Without relativity, navigation fails. With relativity, you know exactly where you are. That's the truth. That's relativity. You age slower when you move. And the universe doesn't care whether you believe it. The satellites still compensate. The clocks still dilate. Time still slows. Because that's how space-time works. Your phone has been accounting for relativity this whole time, keeping you on track, quietly compensating for the fact that time itself bends under motion. You age slower when you move. And your phone has known it all along.